All right, so all the stuff that we did before with that Pogel, that electrons illuminate Pogel, was the work of Niels Bohr. And I don't know if you noticed here, but there's a problem with these dates, right? Yeah, I kind of had him die after, like before he was born. So go ahead and change this to 1962. I know it's not acceptable. He traveled back in time, okay? All right, guys, shh, I'm recording. Time to keep it quiet. All right, so let's fill in some of the things that are here on this paper. That's not good contrast, is it? Maybe. Okay. All right, so Niels Bohr studied the light coming off of hydrogen that has been given energy by electrifying it. Now, you could electrify something, you could heat it, would work the same way. We've talked about that when light is refracted, that light coming off the hydrogen bulb is passed through a prism. That light ends up being split into 4 different wavelengths. There's a red, a blue-green, a blue-violet, and a violet. And this is very much like the graphic that was on the Pogel that we just did. This pattern here that you get from the spectroscope is called a bright line spectrum. So bright line. And we've discussed already that every element has its own unique spectrum. So the spectrum for hydrogen is going to be very much different than the spectrum for helium. And that has to do with the fact that in helium you have different numbers of protons in the middle, and so the magnetic attractions of the electrons is going to be different. What Niels Bohr did is he took those spectroscopes and he measured the wavelengths of those lines and used those measurements then to calculate their frequency. And once he had the frequencies, then he turned around and calculated the energies of each of those bands. Keanu, find your seat. Look for it in a moment. All right, so he concluded that an electron moves around the nucleus in a region called an energy level. And electrons moving around in levels close to the nucleus require little energy to be there in comparison to electrons moving around in levels far from the nucleus. And why was that? When we were running outside in the field, why was that? Because the guys on the outside have to travel a much greater, because of a difference in distance traveled. What he also said was that electrons, like for instance in hydrogen, the electron normally exists here in the first layer. It doesn't necessarily have to be there. Electrons can move between these levels. So when you have an atom like hydrogen, right, whose electron is normally here in the first layer. Excuse me a sec. No, he's in my third period class. That's okay. Bye. All right, when you give this atom energy, whether it's in the form of heat, light, or electricity, that electron is going to move outward. Okay? Now, that layer where that electron normally wants to be in is called the ground state. All right? And where it moves to is called the excited state. So when you give atoms energy, the electrons in the ground state move to excited. Right? As you would be if you were living on the first floor of my building with the cockroaches and you won the lotto and all of a sudden you moved to the 7th floor. You'd be excited too, right? Right. That E with a minus sign is electron. Okay? So electron in the ground state moves to the excited state. So that's the electron going from here to there. Did you get it?
I did.
Okay. That was good. All right, now, that electron that's moved outward doesn't want to stay there. It eventually wants to go back to where it came from. And so when it does that, it's going to give off light, because electrons only have one way of giving back that energy they absorbed, and that's in the form of light. So over here I want you to write, electron moves back to ground. Now, if it takes, let's say, 560 joules to go outward, and I'm making that number up, that could be like not even close to the real thing. When it comes back in and releases that energy, how much energy is released? 560. It's the same quantity, all right? So the energy absorbed and later released is equal in amount. They're just in opposite directions. So in one direction, it would be plus 560 joules. In the other direction, it would be negative 560 joules. And that's assuming the 560 is the quantity that it takes to make that jump. So this is just a review of what we did in the poll, right? Okay, so now, what does that look like to you? The whole scheme. The whole picture. It looks like the solar system to me, doesn't it? Doesn't it look like that to you? Okay. All right, so in Bohr's model of the atom, electrons orbit the nucleus like planets orbit the sun. All right? This model is called the shell model. So like the shell on an egg, except for this egg has 7 shells on it. All right? There are a total of 7 shells. What do you notice about the distance when you're talking about layers close to the nucleus in comparison to ones that are far away? They're bigger. So the difference in energy levels, and there's an E missing there, between layers closer to the nucleus is larger than the difference between layers far from the nucleus. And that's something important to note, especially when we get to Chapter 7 and we start talking about periodic trends. What's that? You don't have to highlight it now. But that's something important that I want you to remember when we get to Chapter 7. All right, so let's flip to the back. Now, the calculations Bohr did only worked for hydrogen. And so that caused him to be ridiculed by a lot of the physicists of the day. He was particularly strongly criticized by Einstein. And the model was also criticized because electrons have no mass. And the picture showing that those electrons are traveling in circles, right? If they have no mass, can you really assume that? The answer is no. The reason why the planets orbit the sun in a circular pattern is because they're experiencing gravity, and they experience gravity because they have mass. Electrons don't have mass. So if they don't have mass, they don't feel gravity, you can't assume a circular pattern. So you can't assume they travel in circles. The other big problem with this model, too, is that it doesn't explain the physical and chemical characteristics of these atoms. It doesn't explain why hydrogen's a gas. It doesn't explain why it bonds the way that it does with other atoms. It doesn't explain why it's highly flammable. It doesn't explain any of that, okay? The last model that we're going to talk about, which starts right here in the notes, does handle that last point, okay? Now, here's the issue. This last bit is going to deal with the wave model, or it's also known as the quantum mechanical model. And at this point, you're no longer going to be held responsible for knowing the experiments that go into it. All right? And partially it has to do with the fact that it really isn't a whole lot of experiments that go into it. It's just like a lot of math. Ridiculous math. that involves statistics and probabilities. It's going to take us a good week or two to really understand what it means. I don't need you to understand the details. I just need you to understand how to apply it. All right? So we're going to go through this really, really quickly. And a lot of this might sound like a foreign language today, but by next week it'll make sense. All right? This is going to be a little bit slow moving as we progress through some of these details. All right, so first of all, in time, Bohr's model was replaced by the wave model. This model is based on complex calculations to describe the location of electrons with a degree of probability of 90%. So it's based on statistics. One of the problems is that when you're trying to figure out where the electrons are and how they're moving, the whole process of measuring the electron messes up how it moves, right? So it's impossible to know the exact location and motion of electron, because when the measurements are made on electrons, they alter the motion of the electrons. So this is an important underlying principle in quantum mechanics called the Heisenberg uncertainty principle. In a nutshell, what it means is that we don't really know what the electrons are doing. We have an idea. It's a pretty good idea. We can be confident with a 90% confidence, but not with 100% confidence. What's still accepted about Bohr's model is the whole idea that electrons are found in energy levels. All right, so we still believe that the electrons are in layers and they have to have certain energies to be there. We just don't believe that those layers are circular any longer. All right, so electrons don't orbit the nucleus in simple, fixed, circular paths. So it's not that here's the nucleus and here's the electron going around and around and around and around in the same path. We think they travel in different paths. Different paths each time. And those paths might not be in the shape of a circle. All right? Instead, how we depict atoms, often what we do is we use cloudy regions known as electron densities. And so what an electron density looks like is, okay, so for instance, here's the nucleus. I'm going to draw a bunch of dots. And as I go further out, the dots get lighter and lighter and lighter. So you have a heavy concentration of dots in the middle. Okay? And that's what an electron density looks like. All right, so what these dots represent is the location where an electron could be. All right? And so the more dots that are in the cloud, the more likely an electron would be to be found there. All right? So in this particular atom, there's a high concentration of dots around the nucleus. That's where we think there's a really high probability the electrons are. And as you go further and further and further out, there's a smaller probability the electrons are there. Okay? Okay. Now, these areas of electron density are also called orbitals. If you have a highlighter, now's when you highlight. Orbitals. You're going to hear that word a lot. And there are 4 different kinds of orbitals. And they have some specific shapes that are shown here. It's unfortunate that this isn't in color. It would be nicer in color. All right. And so, like, this is one kind of orbital. This is another kind of orbital here. This is another kind of orbital. And then this down here is yet the 4th kind of orbital. All right? Okay, so this one here, you need to know that this is called an s orbital. And these exist in energy levels 1 through 7. So on all 7 floors of my building, there's one of these kinds of apartments. And it's a 1-bedroom apartment. What's that look like? A sphere. So I want you to think of S for sphere. That's not really what S stands for. S actually stands for simple. But I want you to think S for sphere, because this is one of the things that you're going to be asked on your next test. I'll give you a bunch of pictures and I'll ask, what kind of orbital is this? And you're going to have to be able to tell me S, P, D, or F. All right? All right, now, so these spheres are on every floor of the building, right? So it's like an apartment that exists on, so it's a spherical shaped apartment, one bedroom existing on every floor, all right? So if you think about it, an atom's just like one inside of another one of these, so it's with a little bit bigger radius, inside another one of those with a little bit bigger radius, inside like nesting dolls, all right? Starting on the second floor and going all the way to the 7th floor, we have another kind of apartment. It's called a p orbital. And if you kind of look at this one here, I think it looks like a peanut, like Mr. Peanut with the top hat on the bottom, like the cans of Planters nuts. All right, so P for peanut. You know those circus peanuts you get? They kind of look like that, have that shape. Okay. All right, then starting on the 3rd floor and working your way up to, let's see, the 6th floor, we start finding a 3rd kind of apartment called a d orbital. D really is not going to stand for what I'm going to have you write in here. D stands for diffuse, P stands for principal, S stands for simple. But like to me, when I look at this, like I think of a daisy. It looks kind of like a flower, right? So I think of D for daisy. All right? It's actually more like a 4-leaf clover, right? All right, and then finally the last orbital that exists is, let's say, like this one down here. There's 7 of these, right? And most of them characteristically look like that, right? These start showing up on the 4th floor and the 5th floor. It's called an F orbital. And to me, it looks like fireworks that are exploding. So think of F for fireworks. Yeah, I think it looks like fireworks. Okay. I know my grammar's bad. Listen, you're lucky I speak English. All right, so I'm going to draw something for you, and then we're going to call it quits. You don't have to draw it, just look. Okay, so I'm going to draw oxygen. Okay, the way Bohr saw it, and then oxygen the way it really is, according to quantum mechanics. All right? So, if we look at the periodic table, what's the atomic number of oxygen? What's the atomic number? 8? Okay. So, in Bohr's model of the atom, you have a nucleus with 8 protons, right? So I'm going to draw a little sphere here with 8 p pluses, right? What did you learn in middle school? That the electrons live in rings, right? If this has 8 protons, how many electrons does it have? 8 as well. How do you place those 8 electrons on the rings? 2 on the first, and then 6 on the next one, all right? Like that? Okay. This is a terrible picture. And I'll tell you why. This picture's flat. Are you and I flat? No. We exist in 3 dimensions, right? So this is not a good, accurate representation of what atoms look like. And I want everybody's eyeballs up on the screen. This is important. Okay. I'm going to draw what it really looks like. Next week, hopefully, you'll be able to do the same thing too. All right? Okay. Really, we exist in 3 dimensions, right? We exist on the X, Y, and the Z. Correct? All right, so here in the middle we have our nucleus. I'm not going to draw it. All right? What I know from quantum mechanics, which you're going to learn to figure out how to do by next week, is that the first 2 electrons that live on the first floor, closest to the nucleus, live in a home that's spherical in nature. All right? So imagine a sphere. All right? Now, I don't know where exactly those electrons are. I'm going to draw them as red dots. I know they exist somewhere in this space. I don't know how they travel in that space. I just know that with 90% probability they're there. Okay? It's like I know that if, for instance, on the weekend, if I call your house, 90% of the time you're probably going to be there. Right? 10% of the time you might not be there. And that's the 10% of the time that maybe you went to the mall, or you went to the grocery store, or you went to a movie with a friend. Right? Now, the next set of electrons live in a layer further out from the nucleus. I'm going to do it in yellow. And two of them happen to live in an area that's also spherical in nature. All right? So I'm going to draw them out here. Again, they exist in this space, but I don't really know how they're moving within that space. I just know they're there with 90% probability. All right, the last 4 electrons live the same distance out as these ones out here, but not in the same shaped home. They actually live in a home that looks more like a peanut. And there's 3 peanuts. There's a peanut on the x-axis. There's a peanut on the y-axis. There's a peanut on the z-axis. All right? And one of the electrons lives there in that lobe, another one lives there in that lobe, another one lives there in that lobe, and another one lives there in that lobe. And again, I don't know how they're traveling in that within the confines of that space, but I know that that's, if I'm going to look for that electron, that's where I should look on the atom. So that's really what an atom looks like. Much, much different than what you learn in physical science. Okay? Now, next week we'll talk about like how this helps us figure out how things bond and so on and so forth. Actually, not just next week. It's for the next quarter we're going to be talking about that. But this is the current view of what atoms looks like. All right? Okay, don't forget homework. What is it again? Cornell notes for 5-1, and then page 132, numbers 1 to 4, and then what's the other page? Page 152, 28 to 21. All right, sounds good. In the back.